we didn't get too far with the Riemann integral, but the key is to define it to begin with. Okay, so we look at the simplest setup. Our rectangle, the domain of our function is a rectangle on the xy plane. We cut both horizontally and vertically where the x and y's equal length, not equal number of intervals, which produces n squared rectangles. Okay, then sample point is chosen for each of these rectangles. And that is the value of the function at that point gives us the height of the bar, kind of a pillar or a box, whichever you prefer. The volume of which we are evaluating. Volume as the metaphor for the integral, even though certainly it is going to have other applications, and that is primarily as a metaphor. So go-to metaphor of double integral is the volume under a surface. Okay, so it's like a box with a curved top. I don't know, a sandbox or something like that. So you have a width on 5 sides and 6 sides might be curved. Okay, so it is given by some kind of surface, surface given by a function of the variables. Okay, so that is, you end up with a double summation. Okay, so I'm trying to remember if in calculus 2 you saw any double summation. Anybody remember? I don't think so. Yeah, so it looks a little bit different, but as long as it is understood what is behind it, and that is an array of numbers. That's what function of variables is anyway. Okay, so it is if we're sampling, that's what we're doing. We're sampling the function to do whatever we want, either to plot it as we have, and it gives the surface, or plot it in a different chart and it gives you bars. Either way, the table or array of numbers, that's where two dimensions come from, in two indices. You just add all the terms there. Okay, so as you can see, that is, I highlighted the chart, and you can see where it comes from. It is, I clicked on the chart and it gives you the highlighted part of the data. On the other hand, this is our S instance for the Riemann sum, and once again it gives you exactly the same square or rectangle of values being added. Okay, so they being added, and then so that we wouldn't have to do too much algebra. Instead of multiplying by 0.01 every time, and then you add them or then multiply by 0.01. The good news is, and that is, I want you to not to be concerned about the issues of calculus. For just this very second, calculus 2 issues, which is convergence. So that is it is wise to be cautious about summations and whether or not you're allowed or not allowed to do certain things with them. This is not a concern of ours because the summation is a finite number of numbers being added. Okay, so literally we can do anything with them as long as we have. We follow the regular rules of algebra. So we're not going to end up with something that does not exist or does not define indeterminate, even infinity. Okay, so nothing of that matter until we take the next step, which is the limit. But for the time being, just like with partial sums of series, everything follows the regular rules of like middle school algebra. Okay, so this sigma notation certainly is something to get used to, but otherwise it's just a summation, and the probably I should demonstrate. So what this summation means, very relevant, is going to be shortly. It is the summation. You could have one summation, and that's exactly what Excel does. So it's just one sum. If you look at what it says over there, it simply says the function is sum, and then followed by the array. Okay, but and that's fine. But when you have a double summation, there is a certain point to it, and that is the order of things. So you could put, you can do it this way. Okay, so as you can see, as always, we read the algebraic expression from inside out. It means that for each I over here, we fix I and then concentrate on summation over j. Okay, so it simply means that in this diagram, this little graph, we are adding these first. One by one, we take a row at, well, which say, that doesn't matter which way. We take a row of bars, add its area, write it down. Okay, we take the next one, add them together, write it down. What is the end result? Is another sequence, finite sequence of numbers. And then we add that sequence together. Okay, so once again, you can say this is for each I. For each I is it is a number. So you can have a separate letter for it, and we might have it already. Okay. So and then in a way it is going to be once we get to computational part of this, it's also will be visible. It is almost visible here as two integrals follow each other. That these so that green thing I put there is kind of optional because once again it doesn't matter. I could have interchanged these. I mean as I hear I went to edit these one, the next. I could go this way, and the result will be exactly the same. Once again because these are finite sums. So which means that's why it's this is optional. Okay, with the and then we see these two sigmas. Sigma stands for sums. S also stands for sum. Stretched S, you get the equal sign, and then you have two of them followed by each other, and that's why sometimes, not sometimes, but we will at some point also see it in this manner, like this. Okay, so the only thing that will remain to be figured out is the limits of integration. So it is very simple. So we're going to do this shortly, but maybe not today. We still proceed with the properties of integrals. They all follow the same properties of Riemann integral from calculus 1. And this is, I guess, this is the notation the most unusual in comparison. So the limits were specific in calculus 1 Riemann integral. So integral, it was always from A to B, right? Fx dx. Okay, so this is the only reason was really is because the simplest building block in dimension 1 is an integral. So that could be written as integral fx dx like this. Okay, it is entirely a matter of terminology. So here it is integral from A to B. That's how we would describe it. Over here, or here, we would describe it integral over intro AB or over R. Okay, so it's the same thing. It's just not specific anymore. The only thing that to keep in mind is the orientation, which we talked a little bit about. So this is with orientation. The terminology from A to B is preferable, not preferable, it's convenient because it gives you the direction of your integral right away. And here, if you just say AB, it might be questionable. So the presumption is over AB means that it is the same as this. Okay. So which means that, for example, if it is in either of these cases, A would be larger than B, and it still works. Okay, with rectangles, slightly more complicated, but not dissimilar, because it is, after all, two squares multiplied by each other, so AD, CD. And once again, you could have, it is possible that C could be larger than D, or A larger than B, and the orientations then, orientations flip. And if we are computing then, orientation meaning the, well, I don't think there's a better word for it for orientation, but the sign of the integral will change just like here. If integral from B to A, versus integral from A to B gives you the negative sign to the integral, and similarly here, if we flip A and B, the sign changes to the opposite, or we flip this one, change to the opposite. However, we change both of them, then the sign remains the same. So that's roughly what orientation means. It is how, if the orientations of the two intervals coincide with the orientations of the axes. Okay, x and y. Okay, so it is presumption that they are, and then if they're opposite, then we have to adjust the sign. We don't have to adjust the sign, but that is the meaning of integrals over rectangles or intervals when they have the orientation opposite of the orientation of the xy plane. Okay, so all right. We did a very simple computation by hand, so certainly a little bit more work than ask Excel to do that, but that should be done once in a while. And then we went with properties. So once again, we don't do any computational business just yet. But this is just the all properties of Riemann integral in dimension 1 have analyzed in for dimension 2. Where do they come from? They come from very simple properties, which once again, thinking about the Riemann sum with the double summation, still finitely many terms, which means that we can rearrange terms any way we like. And in this particular case, we split the term inside, and then do some manipulation and split the whole. This is split together. This is F here, F and G there, and then we recognize each of them as the Riemann sums of F and the Riemann sum of G. And then the last step is just taking the limits of the Riemann sums in order to get the Riemann integrals. And the Riemann, the sum rule for the limits gives us the justification of such a transition. Okay, so we know what the limits of those three are. Why are they related by this equation? Because of the sum rule for limits. Okay, so let's say the magic words here. The Riemann integral is the limit. Then I should have said also then f is called integrable. Over R. Okay, so that we just like in calculus 1, we deal with we have to presume that the integrals make sense to begin. Otherwise, I mean, if it is a limit, the limit might not exist, or it is infinite, and then that will ruin all the algebra usually. So then let me state the sum rule for our Riemann integral. Or let's say double integrals. I dislike the term double integral or triple integral because the only thing that it really referring to is how many of those integral signs you're using. It's not really that we integrate twice. There is one integral, and if we're talking about the areas, then every object has an area. It could be crooked, and it doesn't matter. It will have an area. It doesn't matter where our x's and y's are. It will have the same area. It is intrinsic to the object, and it has nothing to do with the x, y coordinates the way they're changed. Okay, so double integrals or area integrals also a good way to put it. Area integrals meaning the domain. So suppose FG are integrable over rectangle R, then so is f plus g. So I'm talking about certainly here about two functions of two variables. Okay, and certainly there is a relation between the integrals, as we already know. So integral over R f plus g dA is equal to integral R f dA plus integral g or double. Okay, so that's the sum rule for double integrals. Without stopping, let's do the constant multiple rule. Which works out exactly the same way, multiplying the Riemann sum by constant. What does it do? Not much. You can factor it out with no trouble and no need to prove anything. But then when you transition to integrals, that's where the constant multiple rule for limits comes into play. Okay, so say same setup. We have an integral function. Or rectangle again, then so is C f or any real C, and we have a relation between the two integrals, so double integral R CF dA is equal to C is being factored out. Okay. So the two main properties. Trace all the way back to at least a year ago for k equals 1. If you erase the one integral, they stated exactly the same way. Okay, there is one more property that will take extra work, and that is the additivity, which is not the same as the sum rule. So even though you seem to be adding something, but what is being added in the additivity rule? Regions of the domain. Regions, plural. So we're not adding functions, the same function, two regions. Let me first refresh your memory about calculus 1. So it is, well, it's stated there simply as integral from A to B f dx plus integral, let's put a C here, C to B f dx. Same function once again, and but the two domains are possibly, well, not possibly, definitely have one point in common. And then from A to B f dx. Okay, so like this. A, B, C, no. A, B, C. However, the statement itself does not require any particular relation between A and C, which one is larger, which one is smaller. You can go left to right, they could be entirely in the arbitrary order stated. They simply, some of them will be, some of the areas will, some of the integrals will be negative and some will be positive, so it works out just fine. And the idea that is the advantage of calculus 1, what makes it simpler, is the idea of interpreting functions as motion is very much helps a lot, because think about it. What are we talking about? We are talking about the person that had been driving over the time from A to C, then over C to D, and then the question is how much with speed f, or velocity, okay, and then two periods of driving. If you combine them together, then what is the result? Well, you just combine their displacements. So the integrals are displacements, right? So that's the velocity, and then these are displacements. And then certainly if the first hour plus the second hour displacement together give you the displacement over the 2-hour drive. Okay. So a very simple interpretation. Unfortunately, we don't have that anymore. Well, the calculus 1 has two interpretations, and the second one is the area, and that's the one that we can utilize. So this is y equal f of x again, and ultimately remember that the integrals represent or interpreted as areas. So we're just adding the green area to the yellow area, and the end result is the whole area. Okay, so that's the additivity rule, which is simply very intuitively understood at a very basic level. Adding two objects, if they don't intersect too much, then you also add their areas. Okay, so that's what we're saying. And now we are going to do the same with volumes. Okay, so imagine the same picture. We are just looking at that picture on the right. We are looking at from the side, and like this. This is the x-axis, and say about we call this z-axis, and then the y-axis is the one that we don't see. Okay, so and then if we rise above that this xy plane, we are going to see what's happening. And once again, there's some kind of cut of the domain into two. I choose to put a cut along the x-axis. So I'll have not 2 as I have had, but rather I'm going to have 3 intervals on the x-axis, like this. And but still, I'll keep 2 for keep it simple. I'll keep 2 on the y-axis. Okay, so like this. Okay, so choosing the letters appropriately. This is C and this is D. And here I will choose names A, C is taken, so I'll put that Q here. Okay, so that's what we're talking about. Let me mark the 2 domains. So the domains there, the domain, I don't want to confuse. So, okay, no, probably not choose a color, but our domain is this. But you can also think as if you have two functions, and it doesn't even matter what they have to do with each other. If the domain don't overlap, then it doesn't matter. And then above this whole thing, we have surface. Okay, which is also cut in half, or whatever, in the middle, like this, and like this. So it's like we take our sandbox and put a separator, so that you have 2 possibly unequal parts. And so this one, once again, if I try to assign the same colors appropriately, just like in the previous picture, then this is 1/2, the green one, okay? And then the other one is yellow, like this. That is closer to us. Okay, so speaking of the volumes, and unlike those areas, just like those areas, they are represented by integrals. So these will be double integrals. So that picture can be now easily written up as in a manner very similar to that formula. So let me first put double integrals everywhere. dA, we're going to be talking about areas. These are area integrals. Okay, and it's really not about this picture, which is slightly too complicated. It's really about carefully adding the domains. Additivity rule, which means regions of the domain and the integrals themselves. Okay, so adding domain means adding the volumes above them. Okay, unless, well, as long as there is no overlap. Okay, so, and then we have regions. These are the regions. Like this. So, once again, A, Q, B, and this is on the y-axis. We have B, C, and D. Okay, so these are the two that we have to look at separately. The first one, so I'll just write it out what it is. It is AQ cross CD. So this is a big index. It is the domain. It's a biggie, but it's attached to the integral. Okay, so the domain below the integral, as always, I can't call it as a subscript, but it is pretty much what it is. It's easy when it's just one letter. When it's a big one, it's a bit cumbersome. And then the second one, QB cross CD. And the end result is the whole thing. So that's the second one is this. And the whole thing is ABCD. Okay, so that's the additive integral. So that's the punchline. The actual conditions that we still have to say before we start. So we put it there. Suppose f is integrable over, well, once again, AQ, CD, and QB cross CD, then it is integrable over ABCD. And the formula is satisfied. Okay, so one thing is in the why we care about these properties. It's not like we use them a lot for computations. It just helps us to understand what this is to begin with. Before using a tool, we want to know what it is and what it's made of, and to make sure that it is, in some very general situations, it behaves the way we expect it to behave. And this is the additivity of volume. So if you take two objects and the volumes of this, and you create one object from two. Okay, so what happens to the volumes? You add the volumes. That's roughly what it is. And furthermore, if you're gonna want more physical, think about the weight of one object, the second object. You put them together. What happens to the weights? You get the weights. Okay, so that's so far so good. Everything works out as planned. Okay, so now let's try. Let me give you an idea before we actually engage in a more computational part. The idea of how computations are carried out, and I already gave you the idea in the definition, where the double summation can be carried out in two different ways. Okay, so either starting kind of coming like this and then like that, or vice versa. It's like a I don't know, cheese box, cheese cubes. I don't know, they're not cubes necessarily, and you can add them in any way you want. So that certainly is obvious fact that we can see from over here. Let me actually let me do it as a demonstration. So what I'm going to do, I'm going to be adding. I'm going to take. So let me just separate things one from the next. Like this. Okay, so you can see where my table of values is outside of this segment. Everything is the inputs. So you can see the x is here, y is there. Okay. So what I'm going to do is I'm going to add things horizontally, and then the point being, well, like this, and then point being that what we're doing is we're creating a new function. Okay. So over here, once once again, let's create a separator here. Okay, so I'll be putting sums here. Okay, and so literally I'm going to have here equal to the sum of these. Okay, but let's be careful this time. I'm going to multiply by h. Where's my h? Here it is. Okay, so R4C2. Okay, so what is this is? It is the sum of the okay, so you can see the picture at the bottom. The picture at the bottom, it highlights the rectangles over there. The values, and the values are here. However, what I compute is not just the sum of the values, but this time I also multiply them by the width. So in other words, what is that I'm computing? What am I computing? So let's look at the formula again. So you remember what it shows, okay? Well, and then, well, I could probably just plot it. If I plot it. Okay, so these are the values. I created a new chart for the first row over there, and then I computed this. I said sum, but what is really what have I computed? Well,
given z value or given
what is the function?
Oh, it's where y is a constant.
That's right. So in other words, it's a function of one variable. Okay, so y is fixed. No, it's actually x is fixed. Sorry about that. X is fixed on the left at -1 over there. Okay, and then y varies horizontally. Okay, and then which creates what? A function of one variable. We did it when we did partial differentiation. Okay, and then instead of differentiating that function, I integrated. Okay, so in other words, what we have here is the Riemann sum of that function of one variable. And once it is computed, that's what I put here. The Riemann sum of that function of one variable is put on the right. So I put this. I wrote sum there, but really what I'm talking about is Riemann sum. Okay. Okay. So and then I do it for every single row. Okay. So a bunch of Riemann sums for each slice of my data. Of my function of variables. Each slice of this one, it looks pretty much about like this, and then I carry it out and I treat it as a function of one variable. It is already subdivided accordingly along the y-axis, and then the Riemann sum is computed on the right. Okay, so what is the meaning of that column altogether? What is the meaning of this column? What does it look like? There's a correspondence between those numbers and these, right? They're on the same column, on the same row, right? So if the input is -1, the output is 2.87, and then the input is -0.09, the output is 2.471. So what is it? There's no trick question here. It is a function of. It is a new function of one variable. Well, it just happens to look very, very similar. So, except that this function it looks so similar because of the symmetry, obviously. So once again, this one comes from along the y-axis, which we then integrated and produced. We integrated each of the rows, and produced a column of values on the right. Then this column of columns on the right looks like this. Okay, I'm putting it here, except, so this is the function of y, and that is a function of x. The new function is a function of x. And what remains the last step to accomplish the goal? What was the goal?
We just want to multiply it by the our delta A.
Yeah, so in other words, we having this function, which I just happen to plot it in terms of bars rather than a curve, but ultimately with the point being that it's once again the Riemann sum of that new function. Okay, the new function that we computed, and now we have to actually rather than looking at these bars, let's add them together appropriately with the width, and that's supposed to give me the integral. Okay, so what I'm doing here, I will put it here naturally. So I'm writing equal to sum of all these values, okay, and multiplied by, once again, by h, which is R4 C2. Okay, so what is so special about this number?
That's the approximate. Here
It's the same number as before, right? So that number we would compute it by adding all the terms together and look at the formula, and then multiply by 0.01, which is the area of each of the bars, of these bars. Okay. Alternatively, we went first this way, addition, multiplied by 0.01. And then whatever the results are added this way, once again multiplied by 0.01. Of course, if you think about it algebraically, it is exactly the same thing. There is no chance of any other results to come out of it. Okay. It's the same operation. It is just carried out in two different ways. So summation, single summation, or where all the terms run through the array. Okay. Or you do summation horizontally, then vertically, then horizontally. I could have done easily, I could have gone vertically and then horizontally, and then I would end up here with 3.2 to 3.4 just as well. It doesn't make any difference whatsoever. And then that brings me to the ability to compute the integral analytically, because now if we can pull this off, this kind of representation. So it is as if two integrations follow each other, except the first integration is carried out for each x. Okay, for each x, integration over y is carried out to produce a new number, and that creates a new function to be integrated in the usual way. The usual way meaning that it is a function of one variable. Okay, so the first step, going horizontally, integration of one variable with respect to one variable, so calculus 1, and then vertically, once again, a function of one variable. Once again, integration is entirely within our reach based on calculus 1. This is called iterated integration, and so it replaces single area integrals with two consecutive one-dimensional inputs, if you like. Okay, like this. So all you have to do is figure out what the limits are, and you probably can guess easily what they are, considering that it is a rectangle. So if I will be integrating in B, CD like this. Okay. So let me do that once. So integral over R, well, let's write what R is, A, B, C, D. FDA is integral with, I put big parentheses here. One variables here. This time. So I'm using calculus 1 notation, so there will be no doubt. Doesn't matter which one goes first, but right here. X. Okay, so the only difference, so I have y, so it will be CD here, AB. The only difference from calculus 1 setup is that my function f appears to be of two variables, but just like with partial differentiation, that's where you bring your skill from, is to the ability to treat the other variable as constant. And so if I am staying within parentheses, these parentheses here, x is constant. So you altogether ignore it as if, so if you apply constant multiple rule, you apply it, you just pull it out, and you integrate it with respect to y, just like you differentiate it with respect to y, ignoring x, or rather not ignoring, but treating it as a constant. Okay, and then once you're done, the end result of integration with respect to y will be is a number that does not depend on y, but it might still depend on x. Okay, so just as an example of this, so if I need double integral of say xy over rectangle, say 0, 1, 0, 1 d8. Okay, so once you see d8, it's in a way to caution you or stop you from trying to do anything with it, because so you have a function in terms of x and y, and then there's some d8 which seems to have nothing to do with x and y. The reason is because the only way to evaluate an integral like that is to convert it into an iterated integral. Okay, so double. So my regular intervals are clear. They just remember which one is x and y. X is first, y is second. So there will be two integrals with big parentheses. So it will be xy, dy. Y runs between 0 and 1, like this. Okay. Well, once you see this, with just a little bit of experience of partial differentiation, now we are doing partial integration, and I mean we are indirectly right now applying the fundamental theorem of calculus, right? So computing the Riemann integral in terms of Riemann, those two Riemann integrals, or with respect to x and y, and then x, and through anti-differentiation. So, okay, so what do I do first?
We integrate.
Yeah, so I take care of the inside the parentheses first. Naturally. What do I do with it?
Just pull out y.
Pull out y first, right? X. Pull out x first. X is constant, so I put y, dy from 0 to 1. Okay? Just as with partial differentiation. Okay, then, okay, so now I carry out my integration. So x is here, and I'm going to have y squared over 2 from 0 to 1 dx. From 0 to 1x. So I carry it with me until I'm done with y, so I'm not trying to jump ahead. So I plug in y, so it will be 1/2. And, well, dx. Right, so once again, inside the parentheses, that expression, this one, does not depend on y. You will know then you are not to move on to integration with respect to x until the whole expression depends on x only and y is gone. Okay, so 1/2, and I have, I put 1/2 out, and I have x squared over 2 from 0 to 1, and I have, what is it, 1/4. Okay. So that is line by line, coordinate by coordinate integration, which is very easy as long as we stick to rectangles, and which is not gonna, unfortunately. So that becomes way more complicated once our origin from a rectangle with the very easy limits of a and b, of x and y, a and b, c, d. Those easy limits for x and y become much more complicated. The example we already saw, this is in fact what we started with, is the circle. Okay, and then that is a common mistake to jump to from computing the in that manner computing the say any kind of integral over a domain that is not rectangles, and then you end up with limits being just two numbers. Okay, so remember that we went this way from rectangle to the limits, but it works both ways. So if your limits of x and y are equals, that means that your domain of integration is a rectangle. Okay, which means that you're doing something wrong. And if you know what your domain is, and it is a circle, then clearly you should not be having limits like this, constant numbers. So the answer is that the limits will depend on the other variable. So the limit over here, this limit, for example, and that limit possibly will depend, they are with respect to y, and they will depend on x. So this is, as you know, 1 minus x squared. That will be the limit. The limit will be also 0. Okay? So we'll do that next time.